Hey guys, it's Jarret and Quinton. We've written our physics engine and we're here to show it to you today.
Just proving that it can run from my computer.
So this is our physics engine. Let's go ahead and run the simulation first and then explain what's going on.
Okay. Oh boy, she's taking her time.
All right, so as you can see, we've got two balls here on the screen. Their mass is proportionate to, thanks, Quinton. Their mass is proportionate to their radius, so the yellow ball is smaller. As you can see, this motion is not quite perfect, and I'll get into the explanation as to why that is. But there are aspects of this motion that do mimic reality. So as you can see, that yellow ball is clearly on a parabolic curve that's going to get lower and lower with each collision it makes with the floor. That's because we do have momentum enabled. There is a loss of momentum every time there's a collision. In some cases, it looks more accurate than in others, but there is always some loss of momentum. We have a coefficient of restitution for the floor and the walls as if these balls are both made of steel. So the coefficient of restitution for steel is about 0.78. So that's what we're using there. Yeah, so that's, I think it's important that we show the glitches that this system has too, and we'll explain why those exist in a second. But without further ado, Quinton, do you want to start with some of the code?
Sure, yeah. I don't know if we need to show this, but this is just a quick run over of our splash screen. All I'm doing is I'm just drawing it to the screen. And here's everything with like the button. So once it's clicked, it just dismisses it, it goes away, and the program can continue. Kinematics is where we're getting the actual numbers from for our movement. So everything that we're feeding into this class is returning it into animate. And animate is kind of the backbone of everything. This is where the actual setting position to make it move is happening. This is where our checking for whether or not it's colliding with the wall or the floor is happening. And this is also where collision is being handled, which we are also using a some code from Pixel Perfect, which works with SFML to tell whether or not two sprites are occupying the same space using some of the sfrect functions like intersect and contains and things like that.
Yeah, so one of the things we've got going on here is we are calling, so let me jump over to main really quickly if I can.
Oh, sorry about that.
Yeah, so basically here in main, we call these objects, we give them a mass, we give them an initial position, initial velocity, and initial acceleration. And we call this, the typical SFML while loop. Here you can see we call a shape 3.collide and a shape 4.collide. This is where one of our main issues came into play. Basically, there are quadrants on each of these shapes that we came up with. And so what happens is yeah, Quentin, if you want to get us there.
Sure, yeah. Do you want to see?
Yeah, the definition.
So this is where we're actually defining what each quadrant is on the circle. We're drawing little float rectangles inside of the circle. You can't see them, but.
Yeah, so those float rectangles are used in conjunction with the collision library to be able to determine whether or not a collision is happening in certain quadrants of the circle. If there are two quadrants matched up, then we can determine whether it's a left side, right side, top or bottom collision, and we use appropriate functions. If a single quadrant is hit, we use we approximated it as being hit at 45-degree angle to that quadrant. And so that's where this 0.707 comes into place, because it's the cosine or the sine of 45 degrees. So negative or positive, depending on where it's hit from and what the conditions are. One of the issues that we had with this was that the quadrant detection doesn't quite work right. And it has to do with what we showed you back in main, where the collision function is called on each shape one after the other. So once the first collision function is drawn, the second one is then all the signs become opposite. And we ran out of time to fix that. If we had more time, we would write a second collision function that's for the objects that's being tested second. The other thing we would do if we had more time would be to break up these giant functions into smaller ones. Quinton, you want to talk about some of the breakthroughs we had?
Yeah, so I think breakthrough, our major, probably the biggest breakthrough was figuring out how to use pixel perfect and then using it with our quadrant rectangles. That was absolutely massive for pretty much everything that we wanted to do with the collision. Although it might still be a little bit buggy, this was huge. This was kind of the bread and butter of everything we wanted it to be, and I think it turned out all right. Other breakthroughs, I think I learned that there is a lot about this that I don't understand. But I think that's good. I have a lot clearer vision of how this works, but it's still very much shrouded in mystery right now. This was extremely difficult, but it was nice to know a little bit more about it.
Yeah, I agree. There was a lot of satisfaction that came out of blending the nexus of what we've learned in our physics classes with what we've learned in Dave's class. It presented a serious challenge, and I believe through much of it, Quinton literally had to drag me by my hair to get me to participate equally. But I think all in all, we're pretty proud of what we were able to produce. We might have shot a PS5, but I guess we ended up making a Game Boy. That's okay.
But everybody likes Game Boy.
Yeah. All right.
No, that also leads us in then to, does it still align with the original scope, which, kind of. Like you were saying, we got kind of a watered down version of what we wanted, but yeah, I knew this was going to be difficult. I didn't realize the depth of how difficult it was going to be. I just figured it was going to be really hard and we would push past it. But yeah, so the scope is, it's almost there.
Cool.
All right.
Perfect.